Our next speaker is Jinwoo Kim from University of Wisconsin-Madison. He's going to tell us about unrealizability logic.
Okay, can those of you at the back parse my syllables? All right, thanks. So welcome. I'm here to talk about today, not about synthesis directly. I'm going to talk about unrealizability in program synthesis, and specifically how we can prove unrealizability using our new technique called unrealizability logic. My name is Jinwoo, and this is joint work with Loris and Tom from UW-Madison. So before we dive straightly into unrealizability, I'm sure some of you here are not going to be familiar with the concept, so let me just set that in context. So in program synthesis, we're normally given two sets of programs as input. You have a search space and a behavioral specification, where your search space is going to give you a syntactic set of programs that, for the purposes of this talk, we're going to just say is a grammar. So for here example, I have just a simple grammar that gives me assignments to the variables x and y, and the bitwise operators of and, or, and not over values inside my program. I'm just going to call this set BVIMP, and then you have often a behavioral specification that gives you a semantic specification of the kinds of programs that you are interested in. So here, my specification is telling me that I want to synthesize a function f such that it assigns to the variable x the bitwise XOR of the variables x and y. And of course, as we do in inductive synthesis, normally the specification can also be given using a set of input-output examples, as I've just added on the specification over here. Now, given these two sets, in program synthesis, normally your task is to find some f that lies within the intersection of these two sets. And here, I clearly have such an x. I clearly have such an f. I can synthesize XOR using bitwise not and or. But unfortunately, it isn't always the case that I can always find such an f. So for example, here, if from my search space I remove the bitwise not operator and make a smaller set of programs, then my syntactic set of programs is going to shrink such that it does not overlap any longer with my semantic set of programs. So there's no f inside the intersection, which is the set of programs that I'm really interested in, that satisfies both of the criteria that I want. And this is exactly the phenomenon that we call unrealizability. Now, the goal of this paper is really to develop a general proof system for proving that these synthesis problems are unrealizable. And as to give you a bit of motivation of why we want to develop such a proof system, consider that the fact that we are trying to prove that these two sets do not intersect is actually really similar to verification using Hoare logic, where normally you would be trying to prove that a set of states that is reachable from your program does not intersect with a set of bad states. And we're trying to do the same thing here. We're trying to prove that a set of programs from my search space does not intersect with a set of programs from my behavioral specification. And in that sense, we wish for unrealizability logic to provide a basis for reasoning and correctness for synthesis tool, similarly to how Hoare logic is providing a basis to reasoning and correctness for verification tools right now. Okay, so with that motivation in mind, I'm going to tell you why it's exactly challenging to develop such a logic for proving unrealizability, and to see that it helps to understand unrealizability as a logical formula, which actually may look daunting at first sight, but is actually really simple. It simply states that for every program inside your search space, you need to find an input such that your specification is falsified. Now, although the reading of this formula is simple, it does entail a few challenges, such as because we need to reason about every program in the search space, you need to reason about a possibly infinite set of programs, preferably at once, since you're never going to be able to iterate the whole set when you're reasoning about each program one by one. And then, of course, you need to establish that there exists some input that falsifies the specification, where the input can also come from a possibly infinite set. And the additional challenge is that this falsifying input can be different for each program. So the second challenge, that there needs to exist some input that can come from a possibly infinite set, is something that you would also commonly see in program verification. But the first and third challenges, which are that we need to reason about sets of programs, and this input can be different for each program, is something that's really unique to unrealizability logic. So what I'm going to do today is I'm just going to briefly illustrate these two challenges in detail, how we tackle these challenges, and that'll be the majority of the talk, I guess. So yeah, first thing is reasoning about sets of programs. And to reason about sets of programs, like I said, we're going to draw inspiration from Hoare triples. More specifically, we're going to draw inspiration from the principle of overapproximation. So your standard Hoare triple PSQ is actually merely just a statement that says my post-condition Q overapproximates the set of states that I can reach starting from any pre-state inside P and executing it through the program S. Now, we wish to mimic this kind of overapproximating reasoning in unrealizability. So what we're going to do is we're going to introduce the concept of the unrealizability triple. And this unrealizability triple is actually really, really similar to a Hoare triple, except for the fact that your center element, which used to be a single program, is now going to be a set of programs, which I've denoted using the large S instead. So in this case, what the post-condition Q needs to do is that it needs to guarantee that for every combination of pre-state inside P and program S inside my set of programs, large S, Q needs to overapproximate the set of states that I can reach from any combination of these two things. So for example, if I have a singular program S1 within my largest set of programs, large S, this might result in the mint green set of states that I'm currently just displaying over here. And since my large S is a set of programs, I'm going to have another program S2, which can result in a different set of states. And of course, I can also have another program S3 that results in a different set of states. And the idea is that my post-condition Q needs to overapproximate the union of all the states that are in here. So yeah, this is just the principle of overapproximation and how it's applied to unrealizability logic and sets of programs. And to connect this with unrealizability, just shifting these to the right a bit, recall that in Hoare logic, the path of reasoning normally goes is that you want to show that your overapproximated post-condition does not intersect with a set of bad states. And this is because since your post-condition is overapproximating, if they don't intersect with a bad state, then it also means that the set of states that you can actually reach will also never intersect with the bad states. So in essence, what you really want to prove is just P as not bad in as a Hoare triple. And the same story applies for unrealizability logic. It's that given your specification, you want to prove that your post-condition Q does not intersect with your specification. The case is that because we're trying to prove unrealizability logic, your specification, which is normally the set of states that you're trying to reach, are the bad states. So as a triple, you just simply want to prove that P is not spec. And proving this triple is going to give you a guarantee that your synthesis problem is unrealizable. So you want to prove this triple. And of course, another really nice part about overapproximation in Hoare logic is that it allows you to develop all these inference rules that enable compositional reasoning about programs. So like in Hoare logic, you don't reason about a single huge program at once. What you do is you take two smaller Hoare triples for smaller programs S1 and S2. And what you can do is that if I have that PS1Q and QS2R for these smaller programs, I can say something about their composition. I can say that PS1 semicolon S2R holds by the rule for sequential composition. And the reason that this rule holds is because the Hoare triples are overapproximating. The principle of overapproximation is what really supports compositional reasoning. And we're going to do the same thing in unrealizability logic. So we have the unrealizability triple PSQ, and we want to do compositional reasoning for a set of programs. And what's really interesting and exciting is that in synthesis, our search space is given as a grammar. And this grammar really composes smaller sets of programs using operators inside the grammar in a way such that more complex and larger sets of programs are produced by composing these smaller sets of programs. So there's an opportunity for applying this compositional reasoning in synthesis and unrealizability as well. It's just that the same thing, if you have a smaller set of programs, S1 and S2, for example, I just have assignments to X and S1 and assignments to Y and S2, I want to be able to say something about their composition. And because we're using overapproximation as our principle for triples, we can just say the same thing. Given these triples for S1 and S2, we are able to say that P S1 semicolon S2 R holds for the set of programs specified by S1 semicolon S2, where, of course, S1 semicolon S2 is the normal set of programs that you would expect that is produced by a grammar that just contains sequential composition as an operation. So as I said, it's overapproximation plus the structure of the search space that's given by the grammar in unrealizability logic that supports compositional reasoning. Now, compositional reasoning, of course, is a very powerful tool, but as I said at the start of this talk, one of the challenges of unrealizability logic, unrealizability in general, is that you're reasoning about infinite sets of programs. And compositionality alone is not going to be powerful enough to let you deal with infiniteness. So to illustrate this fact, I'm going to give you a simplified example of synthesizing the bitwise XOR problem that I had before. Here, I'm just merely synthesizing expressions instead of trying to assign to variables X and Y. And as my specification, I have as input just a single input output example. I have the input X equals 1 and Y equals 3, and my desired output is 2. And of course, this problem is going to be unrealizable because I don't have bitwise not here. And to prove this fact, I'm going to prove an invariant about all the terms that are inside E. And of course, there are multiple reasons why, multiple methods as to why you can prove this is unrealizable. But the argument that I'm going to go for is since both of my inputs, X and Y, are odd, that is in binary form, their least significant bits are set to 1. No matter how many times I apply their bitwise and or, my output is still going to stay odd. So I'm going to state and prove this fact as an invariant of the search space of the terms that are inside E. Now, of course, since I'm working in unrealizability logic, my invariant is, of course, an unrealizability triple. And this triple merely says that starting from X equals 1 and Y equals 3, which is my precondition, no matter what program is picked inside E, the resulting value, VE, is always going to be odd. I'm just using VE as an auxiliary variable to capture the output of evaluating expression here. So I'm going to prove this in a process that's essentially identical to structural induction by using the two rules that I've listed below, which look scary, but essentially just introduces an induction hypothesis into the context gamma, and also applies an induction hypothesis that's already inserted into the context gamma. So it's the same thing that you would do for structural induction. So the actual proof tree is going to look something like this, where since I'm trying to prove my induction hypothesis, I'm going to start out with an application of the hypothesis rule. I want to introduce the purple triple, the thing that I want to prove as an induction hypothesis. And this is going to generate these 4 proof obligations, which are actually generated by the productions of the grammar. So when applying this rule inside a proof tree of unrealizability logic, you have to look at the grammar, and you have to take the productions, which are actually your cases when you're doing structural induction. So clearly, my gamma contains the single hypothesis that I'm trying to prove. And my I is just shorthand for the input, X equals 1 and Y equals 3. And my O is just shorthand for my output, VE is odd. My output is odd. So clearly, X and Y are the leaps from the production, and these are the base cases. So I need to prove these without applying the induction hypothesis. And thankfully, in this case, it's really easy to do so, since my X is guaranteed to be 1, and clearly 1 is odd. Same thing goes for Y. So that's how you prove that the hypothesis is valid on the base cases. A bit more interesting is the inductive cases, which are given by the recursive productions of the grammar in general. For example, taking E and E, I have 2 applications of E, one on the left and one on the right. And in both cases, I can just simply, in this case, invoke the apply HP rule, which will allow me to take the hypothesis that's inside my context and prove it for free. So this is exactly what you would do when you were inducing the induction hypothesis in a proof of structural induction. So that's how we can prove that the output remains odd for the case of AND as well, and of course for the case of OR as well. So we've established essentially that X equals 1 and Y equals 3, E, output is odd, holds as an invariant over the search space E. And as I said a few minutes earlier, the final reasoning step is that since all programs in E result in odd values, that like we've just proved, the desired output is even, so we're never going to be able to reach the desired output. So the problem is unrealizable. So this is how you would complete a proof tree in unrealizability logic dealing with infinite sets of programs. So you'll notice that the example that I have here actually just relies on a single input-output example. So the second challenge that I'm going to deal with is synchronizing between the possible multiple input-output examples that you might have. So as I said at the start of this talk, to prove unrealizability, you really need to establish that for every program inside your search space, there needs to exist an input that falsifies the specification, and this input can be different for each program. And this is, of course, not a straightforward fact to prove because of the behavior of having multiple programs inside both your search space and your input-output examples, as I'm going to illustrate in this example. So here I have a synthesis problem where my goal is to set the value of x to that in y. Simply just synthesize x as y. As my inputs, I have x equals 0, y equals 1, and y equals 2, and y equals 3. I have my desired outputs, and in my search space, I have 3 programs, x equals 1, x equals 2, x equals 3. So clearly, this problem is unrealizable because I can only assign constants to x, and the value of my y changes. So there's no program inside the search space that works for all of the examples. But if you do a naive computation of all the outputs that you can achieve by taking a combination of input and search space program, this is going to suggest that the problem is actually realizable. And this is because of the naive computation that we did before. It fails to account for the fact that the inputs of the synthesis problem should actually execute the same program, which is expressed using dotted red lines when creating the outputs. So the solution to this is really simple. We're just going to vectorize the input examples into one, such that all inputs are forced to execute the same program simultaneously. So here I have like a vectorized input where instead of having 3 separate examples, I have one example that's vectorized using subscripts. Similarly, I have a vectorized desired output. And if you compute the set of states that this vectorized input results in through the search spaces of the program, it's going to be clear that the x's are going to be set to the same values. So at this point, it becomes clear that the set of actual outputs does not contain the desired output, and thus the problem can be shown unrealizable. Now, we do use vectorization as the solution to the synchronization problem in unrealizability logic, but since vectorization requires moderate changes to the semantics of programs and stuff like that, there are several issues that vectorization also brings up itself. For example, if you're doing vectorization with if then else, then you need to ensure that different examples inside a single vector take different branches. If you have multiple vectorized inputs, which can occur when you're completing a proof tree and you're in the middle of trying to deal with something like sequential composition, then you need to figure out how to synchronize synchronize multiple vectorized inputs with multiple programs from the search space. So I'm not going to go into the gory details about how we actually achieve this, but there are a few clever ideas, and one of the really nice things is that all of these ideas are captured cleverly as predicates for the inference rules of unrealizability logic. So I hope that adds to some advertisement to the paper. So to wrap this talk up, I'm going to talk about some applications of unrealizability, just in case you're skeptical after hearing this talk as to why you would want to go through such a complex system to prove unrealizability of synthesis problem. After all, I mean, it seems that synthesis is easier. You can go about synthesizing programs. Where would I want to use unrealizability? And well, unrealizability actually has a lot of applications, one of them being synthesizing optimal solutions to programs. So for example, if I have a search space S, if I want to synthesize the optimal solution to some specification, what I would do is first I would synthesize a solution to this here, and then I would shrink the search space such that the search space no longer contains my previous solution and any other solution that is on par with the solution that I synthesized before. So in this case, the extra synthesized solution from the next step is going to be more optimal than the solution that I synthesized before. And then I can repeat this again and again until I finally shrink the search space enough such that my search space no longer intersects with my specification. And at this point, then I can guarantee that this is an optimal solution because I can prove that the problem is unrealizable with the search space S up 4. So with proving unrealizability, I can also prove the optimality of my synthesized solutions. One other application of unrealizability is in symbolic execution, where you can prune spurious path constraints that do not fit with your patches that you're trying to synthesize in the context of program repair. And one other place that you might unrealizability is in the context of actual program synthesis. Everyone is actually doing this already in top-down synthesis, where you are trying to synthesize programs top-down. You have your search tree, and you want to find out as quickly as possible whether this search tree is going to be a viable solution to your synthesis problem or not. I mean, like 30 minutes ago, we were pruning partially validated expressions away because we knew that those expressions would not result in the values that we were looking for. And that's unrealizability right there. I mean, it's something that everybody's been doing in program synthesis. It's just that we haven't been studying it under the idea of unrealizability. So as the final slide, I'm just going to display this as a teaser for what's in the paper. And that's going to conclude my talk. Thank you.
All right. Questions over there?
Very nice talk. Thank you. My question is mostly about the motivation. So the example is about bit vector with several traditional bitwise operators. But in many other settings, you have if then else, right, for any traditional programming language. So if you have if then else, and if you do program by example, you have synthesis from examples, it's always realizable, right? If you don't care about overfitting. And if you don't care about overfitting, what makes sense is to limit the size of the program, and then the realizability problem becomes trivial. We just search over a finite space, right? I think the question is for more general context beyond bit vectors. What could be the applications of this work?
So I'm not exactly sure that I got the latter part of the question. I did understand until the fact that if you have if then else and you have like a finite number of examples, then you can synthesize anything. So what was the question after that? I'm sorry.
I'm just asking about the motivation. What's the possible applications in the context that you have if then else?
In the context of like a program analysis, I'm sorry?
No, I mean, if you have if then else, then will the unrealizability problem just becomes trivial? And
No. Even if you have if then else, there are problems that are unrealizable. Especially, I mean, like if you have an unlimited number of if then else's and you have only a finite number of examples as your specification, then yes, it becomes trivial. As you say, it's always going to be synthesizable. Well, not always, because that also depends on the kinds of conditions that you can synthesize and the bodies that you can have inside the if then else. So no, I don't think it's trivial. And even like in the setting that you have an unlimited number of if then else's, and even in the setting that you have an unlimited number of if then else's, you can't say that you can synthesize everything, because if you have an infinite number of examples, like given to you as a universally quantified logical specification, then you would need an infinite program to cover all of those examples. And normally when you're trying to program stuff, you don't want an infinite program. So unrealizability logic, what it does, it also guarantees like the non-existence of a finite term that satisfies your specification.
Okay, so just a follow-up, do you have if then else rules in your proof system?
Yes, I do have rules for if then else, but let me see.
I think the main point is that they can handle not just finitely many examples. They can handle infinitely many examples and also specs beyond examples, and that's
yes
makes it still relevant, right? Okay.
So yeah,
I think in the interest of time, we should move on to the next question, if there is one.
it looks like this, by the way.
Okay, hi. Hey, that was a great talk. So it seemed like in your example there, one of the hard parts was really coming up with this invariant that sort of characterized, the space of the realizable space. Can you comment? I sort of see this as being integrated into an automated system. Maybe you have some ideas about how you might do invariant inference in that space. Have you thought about that at all?
Yeah, so like figuring out the invariance is indeed, I mean, it is one of the hardest challenges to automating unrealizability logic, since you do need to figure these invariants out if you want to have any chance of automating this. So there is a theorem that we have that there is a theorem that states the existence of a good invariant for every condition that we're trying to prove. And that's the existence of that invariant is what's related to the completeness that's listed over there. So I can say that the invariant does exist, but I mean, aside from the normal approaches that you would try to find such invariants, like Craig interpolation and stuff like that, we haven't tried any specific techniques for finding invariants over sets of programs. So yeah, that remains future work.
Can I ask a related question? Is
Sure.
there something like a weakest precondition just for composition, so that you can synthesize for composition the predicate that you need? Well, when you're doing S1, S2, right, you got to come up with the intermediate predicate that describes you have P and Q, but you need to figure out R. And usually that's done by calculating a weakest precondition. Is there something analogous here?
So I think the language that we consider in our paper is limited to simple assignments and expressions. So since everything atomic is going to be an assignment, the weakest precondition that you're looking for is the rule for assignment. And in this logic, we actually don't use weakest preconditions. We use strongest postconditions. But yeah, we have strongest postconditions for every atomic language feature. So I think that you start from that, and then, like we said, we build the proof up compositionally.
All right, we are out of time. Let's thank Jinwoo again.